Mm-hmm.
Hello everyone, I hope you're doing well. In this video, we are going to solve a problem related to volume density or theoretical density or simply density of ceramic structures. So they are all equivalent terms. They are same. So if any of these terms comes in, so you should know that they are all same. And yes, let's see the problem statement and we'll dive directly into the solution. The statement says that compute the theoretical density for sodium chloride. How does this compare with its measured density? So what we need to do in here is that we need to compute the theoretical density, which is actually the volume density for sodium chloride. Sodium chloride is actually the ceramic structure in here, and you must know that sodium chloride is most frequently studied ceramic structure in solid state physics, chemistry, physics, and everywhere. Okay, so we should know everything about it, and we need to compare the result that we are gonna get for the density theoretically with the experimentally determined density. Okay, so there is a value of density that we measure experimentally, and this is the value. It's 2.16 grams per centimeter cube, and this is the experimentally determined density. Let's see what we are gonna get theoretically, and let's quickly get started. As we have seen that what we are actually gonna calculate, its volume density simply. In solution, we'll write the formula first. We know that volume density the volume density of ceramic structures is given by density of ceramic structures, crystal structures, is given by following formula. Let's write down the formula. So we represent density by rho sign, and we can put V in its subscript to show that it's the volume density. Sometimes we have planar density, linear density, so it's volume density, and it is given by N prime into A of cation plus A of anion, all right, divided by product of volume of unit cell times Avogadro's number. All right, this is the general formula. Let me call it as equation number 1, and we'll be using it to calculate the volume density in our case. And let me tell you what does each of these terms mean. Here n prime is actually the number of formula units in a single unit cell. Formula units in a unit cell. We know that ionic compounds have formula units, and it's actually the net number of NaCl pairs we have inside a single unit cell. All right, and I'll tell you what it equals to for NaCl, and then AC is actually the sum of atomic weights of all cations in a unit cell. It is actually equals to the sum of the atomic weights of all the cations present in a unit cell. Since we have NaCl structure in here and we have only one kind of cation in here, so it's actually equals to the atomic weight of sodium. And if we have two different kinds of cations, so you have to sum up the atomic weight of those two cations. For example, if it's sodium and potassium as well, so atomic mass of sodium plus atomic weight of potassium, that will be actually this thing. Okay, that will be the net sum of cations. Then we have anions. It is actually the atomic weight of anion, net atomic weight of anions. In ceramics, we can have a number of different kinds of atoms inside a unit cell, and we can have more than one cations and more than one anions. That is why we are saying that sum of the atomic mass of all the cations and net atomic mass or weight of all the anions in a unit cell. Sodium chloride is the simplest one, in which we have a one cation and one anion. Vc is the volume of unit cell. Na is the Avogadro's number. Avogadro's number. Let's see how we can do it for sodium chloride. And we know that you don't need to write all of these things in neat form when you are solving this problem. I just told you people so that you may be familiar with what each of these term means. Okay, so that we can insert the values accordingly. You should first know that what this each of these thing means. And we know that for sodium chloride, the net number of formula units in a unit cell is actually 4. Okay, and sodium chloride is also known as rock salt, and its structure is also known as rock salt structure. In the later problem, they might tell you that the following compound, for example, XYZ compound, has a rock salt structure. So you are supposed to use n prime equals 4, like the net number of formula units will be same because it is specific to the kind of structure the compound has. So we are going to use n prime equals 4. And atomic weight of cation, is actually equals to the atomic weight of sodium because it is the cation, and it's 23 grams per mole, and specifically it is 22.99, but I'm using 23 grams per mole because it's fine. And atomic mass of anion is actually the negatively charged ion, and it's chloride here. All right, so we can put the atomic weight of chloride, which is 35.45 grams per mole, and you have to remember them until unless your tutor just agrees to give these values in paper. Okay, if they don't, you have to remember them because it's something that most of the students used to remember. And next we have Avogadro's number, which is equals to 6.023 multiplied 10 to the power 23. All right, next we have the volume of the unit cell. And volume of unit cell, we know that the volume of the crystal structure of NaCl is FCC cubic each. NaCl, Na separately makes FCC structure, chloride ions also makes a FCC structure. So they resemble a cubic structure, so their volume is also equals to A to the power 3. Here A is actually equals to 2 times radius of sodium plus 2 times radius of chloride ion, whole cube. Okay, so A, which is the lattice parameter of NaCl structure, is actually equals to 2 RNA, which is sodium ions radius, plus 2 times the chloride ions radius, and whole cube. That is the formula for the volume of NaCl. Okay, all those structures which resembles the NaCl structure will have the similar formula for the volume. Okay, like 2 times the radius of cation plus 2 times the radius of anion, and whole cube. That is the formula, and we'll see another example as well. And let me mention the radius of sodium ion, which is actually equals to 0.102 nanometer, and radius of chloride ion, that is equals to 0.181 nanometer. Hopefully they will give you in question because you can't remember all the values, so you can ask it from your tutor. They should tell you these values, these constant values, if you don't remember it. So I'm gonna use 0.102 nanometer is actually equals to 10 to the power minus 9 and meter, and I want to convert it into centimeter because the result that I want to get is in centimeter cube. Okay, grams per centimeter cube. That is why I'm gonna convert it into centi, and we know that centi is actually 10 to the power minus 2, and if I separate minus 2 from minus 9, we are left with minus 7. So we can divide the power minus 7 and minus 2, and we can write it as 0.102 multiplied 10 to the power minus 7, and it's 10 to the power minus 2 is centi, so we can write centi here and meter, and it's 0.102 multiplied 10 to the power minus 7 centimeter. That is the value that I'll be putting. And here similarly 0.181 multiplied 10 to the power minus 9 meter, and we can write it as 10 to the power minus 7 into 10 to the power minus 2 meter. Centi is actually 10 to the power minus 2, so we can write centi in place of it. So it's 0.181 multiply 10 to the power minus 7 centimeter. Alright, so we can see we have quite a lot of things for the data, and let us calculate the volume separately so that we have fewer complications while finding out the density. Putting values into V, so V equals 2 into R Na plus 2 into R Cl minus whole cube. Let's insert the values. As I told you people, we'll put the values in centimeters, so it's 0.102 multiply 10 to the power minus 7 plus 2 multiply 0.181 multiply 10 to the power minus 7 and its whole cube. Let's calculate it on calculator and see what we are gonna get. And well, this is the value that we got. It's 1.81 multiply 10 to the power minus 22. So it's 1.81 multiply 10 to the power minus 22 and it's centimeter cube. As I told you people, we put the value in centimeters, so the cube of it is centimeter cube, and that is the volume. Now let's put the value in equation number 1 here to get the volume density. So volume density is given by we can write rho v equals n prime. We can write A of sodium, ion, we write it in ionic form because they are representing cations and anions, and volume times Avogadro's number, and we have n prime to be 4. It's 23 plus 35.45 divided by volume, which is 1.81 multiplied 10 to the power minus 22, and Avogadro's number, which is 6.023 multiplied 10 to the power 23. Yeah, let's calculate it on calculator and see what we are gonna get. You can see the result is 2.14. It's 2.14 and it's in grams per centimeter cube. Okay, grams because the molar masses, the atomic weights that we put in here are in grams per mole units. All right, and that is why we have grams in here, and it's centimeter cube because of what we did with volume. And that is the volume density. The theoretical density, this is the theoretical density for sodium chloride. For sodium chloride, the experimentally determined, the experimental value is 2.16 grams per centimeter cube, and we can see rho v, the theoretical density, is close enough. You can also find out the percentage error between these two values, and percentage error between them is actually given by 2.16 minus 2.14. okay, the experimental value minus the theoretical value divided by the experimental value multiplied by 100. okay, let's see what we are gonna get. So this is the error percentage, which is 0.88%. 0.88%. This is the percentage error between the theoretical density and the experimental value, and it's 0.88%, which is less than 1%. So the error is less than 1%, and that's a acceptable error. We can see it's really small. The error, the percentage error is less than 1% between the theoretical density and the measured density. All right, so that is it for this video. I hope you got it, and if you do, then keep watching. I'll be uploading more of these videos, and stay tuned. Goodbye.